All right, hi everyone. Welcome to our last talk of the seminar this term. We'll start again from mid-January. Today we're very happy to have Mina Dalirrooyfard from Morgan Stanley Machine Learning Research here. Come and tell us about computing graph codes privacy.
Great. Thanks, Sapir, and thanks for inviting me. Yeah, so I'm going to talk about a lot of different graph cut problems in the differential privacy world. Okay. Great. So this presentation is work with really nice collaborators from these three papers mainly. And my slides are mostly taken from Slobodan's and Justin's slides, so credit to them. And yeah, so my goal is to kind of give you the idea of like our main results. I don't want to like give you a full proof of anything because a lot of privacy proofs just include a lot of like math to make it work, but just want to give you like the main observation that kind of made us overcome all the challenge. That would be my goal for all of the results. Like any differential privacy talk, I have to have kind of like a motivation slide or like kind of an anecdote. So it's not like these like kind of privacy breach anecdotes made differential privacy happen, but they probably made it more popular. So what happened here was that in 2013, so it's actually quite old, the New York City taxi, they published this data that they put for a lot of rides, they put like the pickup location, drop-off location, the fare that was paid, and if any tip was paid on it. And like they said, they anonymized the license plates, the name of the passenger, etc. And I think this was basically done for just like research purposes. And what happens in a lot of these like basically privacy breach stories is that people find other data that is other data sets that are public and cross-reference them, and like they basically find some private data that was supposed to not be found in there. And specifically, they found that Bradley Cooper, like one of Bradley Cooper's trips and one of Jessica Alba's trips. And like the controversial thing was like Jessica Alba had a $9 trip, but she didn't pay any tips. And yeah, so it basically like makes a lot of these types of information public. And yeah, like I said, this didn't make differential privacy to be a thing. Differential privacy was defined before a lot of these like incidents. It just made it just maybe a bit more popular in practice and generally also in like research. So let's define it. What is differential privacy? The general idea is that we want a private algorithm to output similar, like basically similar things on similar data. Okay. How do we formalize that? So we begin with what do we mean by similar data? We define that by the notion of neighboring data sets. So neighboring data sets differ in only one entry. And in the graph world, which is what this talk is going to be about, two graphs on the same vertices that differ only in one edge are going to be neighboring. In the unweighted graphs world, this is quite clear. So for example, here on the right side, the nodes are all the same. The edges are all the same, except for the red edge that exists in one and doesn't exist in the other. If we have weights on the edges, then there are like a few different definitions. One that we're also going to use is that, again, vertex set is the same. All the edges are the same with their weights except for one. And the weight on this edge in the two graphs differs by only one. Okay. And the good thing is that I'm going to like get into the definition of cut problems, but in the cut world, like you can treat non-edges as edges with weight 0. So that makes the definition quite nice and easy. Now, what is a differentially private algorithm? We say that A is epsilon dp if for all neighboring data sets X and X prime and all outputs O, the the probability that A outputs O on input X and the probability that it outputs O on input X prime is roughly the same thing. And this roughly the same thing is characterized in this ratio being in the interval of e to the minus epsilon and e to the power of epsilon, okay? So this is called, in fact, pure dp. A slightly weaker notion is approx dp. So there's now another parameter delta. If delta is 0, this is going to be pure dp. So this is just like another way of writing that equation above. But now we have this slack delta. So this error value delta that you can look at it like a failure probability that like the privacy fails, okay? And this delta is usually really small. It's like 1 over poly of size of the input. So it's usually really small. But sometimes we can't avoid having it. Okay?
There is some phi missing in the bottom.
What do you mean?
The right-hand side of the inequality means AX prime goes to the AX.
Oh, yes, yes, yeah, yeah. It's X prime, yeah. Yeah. And the other, yeah, either X prime can be on the left or right. Yeah, you can change them. Like it's either the probability of the output of A on X equals to O is less than some coefficient times the output of A on X prime equals to O plus delta, and you can also just change X and X prime again because it doesn't matter. Exactly. If you said delta 0, you should get the above. Yeah. Are we good with the definitions? Great. So there is usually a privacy accuracy trade-off. So if your epsilon is larger, that interval gets larger, so you have more room for these probabilities to differ. And this means that you have basically a lower privacy, but you can have higher accuracy. And vice versa. Like if your epsilon is smaller, you have higher privacy, and usually it means you have lower accuracy. And usually the question is like, okay, how can we get the best of both worlds? I want to have like, I'm gonna have a quick slide on the techniques so that we're like on the same page. It's like really basic techniques that are used almost in any like differentially private algorithm. So let's say that we want to output some values privately, and I have a example here. So for example, the problem here is outputting the sequence of degrees. Okay, so the degree vector of our graph. So we have 5 nodes in this graph, and like the degrees, I just like put the degrees in one vector, okay? And the red, so I have 2 graphs, 2 neighboring graphs. The red numbers are the nodes, the degree of the nodes that differ in these two graphs. It's because of that red edge, basically, right? So we want to output this degree sequence privately, meaning that we kind of like when we give these 2 graphs to our algorithm, basically kind of outputs the same thing, like with high probability. Let's like look at it that way. Or like the distribution of the outputs on like these 2 graphs, we want it to be the same. So what do we do? Like intuitively, we want to add noise. But then the question is, okay, how much do I add noise to these numbers? And this is quantified by 2 main parameters. One is our epsilon, and the other one is this parameter called delta. It's the sensitivity. What is the sensitivity? So it basically says when you go from one graph to a neighboring graph, how much your values change. Okay. If basically the intuition is that if when you go from one graph to a neighboring graph, your output changes a lot, then you probably have to add a lot of noise. But if it doesn't change a lot, then you can get away with adding a little bit of noise, okay? And so there are like, well, 2 most popular ways kind of to draw this noise. One of them is called Laplace mechanism. So you draw the noise from Laplace with parameter delta over epsilon. And what you do is that, for example, in our example, for each of these entries, you draw noise from this distribution and you add it to the degree, okay? And you have another way as well, use basically normal distribution, Gaussian mechanism. And again, the parameters, yeah, the parameters depend on delta and inverse epsilon, in fact. And you can see again that privacy accuracy trade-off, like epsilon, when epsilon is larger, we can get away with smaller noise. When it's smaller, the noise is larger, and delta as well. Now, one question is like, okay, why would I choose one over the other? And like the rough answer is, this is not like a rule, but generally if you're computing your sensitivity using L1 norm, you use Laplace. If you're using L2 norm, you use Gaussian. These are the details that like you don't need to know, but if you're just interested in like, why would I choose one over the other? Yeah.
How do you measure the change in the outputs? Is it just?
For example, these are two vectors, right?
Yeah.
Like, look at the distance between these two vectors, for example, right?
So do we see any output as a vector?
Like, for example, if I was just outputting one value, then it's like a vector with one entry. That's like, you can use either of these. L1, L2 doesn't really, differ. But if you're outputting multiple values, you can, see them as a vector, and then, you can use different norms, etc.
Is it delta square in the Gaussian mechanics? Yeah.
Sorry.
It should be delta squared in the study.
Yeah.
Because it's like standard deviation.
Yeah,
variance.
yeah, right. Yeah, thanks.
So expected value of Z is 0 even for long loss?
Yes, yeah. Okay. And if we want to output objects, one way to do it is called exponential mechanism. And I'm not going to define it formally, but I'm going to mention it a few times. So I just want us to agree on roughly what it is. What it does is that it assigns probabilities to each object in the universe, and then basically picks one object and outputs it according to this probability. Now, where does this probability comes from? We give each of these outputs a score, and this score is based on how accurate this answer is. Like if I output something, is it like close to what I wanted, like the actual answer or not? And it also has some measure of sensitivity in that score as well. Okay. So these were kind of all the most popular techniques, I'd say. I'm gonna next get into graph cuts if there are no other questions. Okay. So you've probably all heard of graph cuts. A cut is a bipartition of the vertices of a graph. We show it specifically in this talk by just a set of one side of this cut, like S. And the cost of a cut, which we show by W of S, is the sum of the weights of the cut edges. So all the edges that go from one side to the other. And so the minimum C-cut problem, which again is, you probably all have heard of, is the minimum cost cut that separates S and T. And it has like a lot of applications. Probably I have a theory audience, don't need to promote it a lot, but like it's used as a primitive in a lot of different problems, like clustering, a lot of graph algorithms, etc. So I'm going to talk about, in particular, 4 different cut problems. I just want to like quickly go over their definitions so that again, we're all on the same page. So the first one is global min cut. So we want to like output a cut that has the minimum cost over all cuts that are non-trivial. So they have like both sides non-empty. Minimum C cut, we just talked about. It's basically, I want to output a cut that minimizes the cost over all the cuts that separate S and T. And notice that I'm outputting cuts here. I'm not outputting the value of like these minimum cuts. I want to output like a set of nodes here. The all pairs min cut, or all pairs min C cut, basically it's min C cut now for all n choose 2 pairs of nodes. Okay. Again, I want to output the cuts. Okay. And the last 2 are basically the same problem. It's differentially private all cuts. So In the all cuts problem, I want to output a data set. Now I've written here synthetic graph because that's what we do. But it can be basically any data set that you can then query the value of any cut. So any cut as in you give it a set of nodes and you're asking what is basically approximately the sum of the weight of the edges that go outside this set. And there are exponentially many of them. So why are we like phrasing it this way, that we are outputting a synthetic graph or a data set? Because there are exponentially many of these values. You can't just like efficiently output a list. So you need to have a way of querying them. And yeah, these last two rows, I just want to differentiate between allowing multiplicative error or not. But for all the other problems, we're not allowing any multiplicative error. Okay. So yeah, what do we know? This is not like a complete list of like all the results and papers. It's kind of the best that we know for each problem. So for the first problem of global mean cut, this problem was solved like in 2010 by Gupta et al. They gave an algorithm that gives an additive error of order log n over epsilon, and they showed that this is optimal. It's the best you can do. Yeah.
You're outputting a set.
Yeah.
Such that the value of the cut is more than log n over epsilon.
It's at most, yeah, log n over epsilon.
This set is differentially private or changing a single edge.
Exactly. Yeah. Okay, then for a mean state cut, that's the first result I'm going to talk about. We give an order n over epsilon, an algorithm with error order n over epsilon, and we show that it's also essentially optimal. We can't do better than that. And I'm going to talk about why this gap when we go from mean cut to mean state cut, this huge jump in additive error. Then for all pairs mean cut, we show that we can get away with like a polylog n factor in our error when we go from mean state cut to all pairs. Okay, it doesn't explode that much. And the lower bound that we had for mean state cut carries over for all pairs mean cuts. So it's kind of optimal, nearly optimal. For the problem of all cuts, there is this work by Elias et al. And then Lee et al. Kind of like enhanced it. And they say basically they can output a synthetic graph where you can query any cut, the value of any cut there, and the value that you get is at most root mn over epsilon off from the actual value. Okay, what is m? M is the sum of the weights of all the edges in the graph, because our graphs can be weighted as well. And they say that if you don't allow any multiplicative error, this is the best you can do. Like, this is it. That's a good question. I don't exactly remember what their instance was. It may have been just dense, but yeah, I don't remember what like specific instance they had, if for all M or not. Yeah. But the thing is that they're not adding any multiplicative error, but if we allow a little bit of multiplicative error, this lower bound is not going to work. And so then we were like, okay, what can we do? Our last result is that we can, so that previous result, when you put m equals to 1 squared, when it's a dense graph, let's say you get n to the 1.5. And we're like, okay, let's beat that if we allow multiplicative error. And we can get like order n to the 1.25. And the lower bound of omega of n still carries over here because that lower bound in mean state cut, that still holds even if you allow multiplicative error. And so if you can query all cuts, you can also find, well, it's not strictly true, but you can basically make it work for finding mean state cut. Okay.
Question
Yeah.
or two about this. For the first three rows, is it no multiplicative error?
Yes, no multiplicative, yeah.
Also, which of these results are computationally efficient, if any?
They are all computationally efficient, yes.
Okay.
So one other question about Gorman, what does it mean when the epsilon is not stated? As in, is it for epsilon equal 1 over 10, there is something like that?
Yeah, it's like that, yeah. Yeah, like if epsilon is, yeah, less than, yeah, there is like a bound on epsilon, and for that, no, it's not like for that. It's like, yeah, basically you can't show the dependence on epsilon. No, the bound on epsilon is not like, yeah, if epsilon is like too small, then you can't do better, because that would be like,
But if epsilon is 1 over 2 to the n of something is
no, yeah, epsilon is usually constant. Yeah.
But the running time of the DP outcome, no multiplicative error is very high. It's high order polynomial.
Yeah, it's still polynomial. It's efficient in the DP world means not exponential. So for example, even for, yeah, the DP min cut, well, okay, I've put out some like details just to not make the table overcrowded, but that result, if you're considering pure DP, that is exponential time. If you're fine with approximately, it's gonna be like n to the 7-ish. So it is efficient, but yeah, but you're gonna get approx DP in fact. So I'm gonna talk more about that in my open problems slide, but yeah. All the other ones I would say are mean state cut. I'm gonna talk about the algorithm. They're like order n or n squared. They're like more yeah, the type of basic time complexities we're used to, let's say.
And if you look at computational efficiency and run exponential and n is among all whatever trees have n log n trees.
Yeah, you can do those things. Yeah. The main goal is like, yeah, to have it like efficient, but yeah, if that is hard, then yeah. Okay, so the first one I want to talk about is the lower bound result, in fact. So in a lot of the lower bound results, first, before I get into that, I promised I'll talk about the gap between mean state cut and global min cut. So I'm claiming that mean state cut needs omega of n additive error, but I said that we can there's an algorithm for global min cut with additive error order log n over epsilon. So why such a big difference? These problems may seem similar, but they're in fact very different, and it's due to Karger lemma. So Karger lemma says that there are at most order n to the power of 2c many cuts within c approximation of global min cut, meaning that like there are not, if you're like fine with like just outputting a cut that is close to min cut, you don't have exponentially many, you have polynomially many choices to like choose from. And then that makes it easy to run exponential mechanism on it. And that's exactly what they do. But the problem with mean state cut is that there can be many, like basically exponentially many mean state cuts, not even approximations, just mean state cuts. So the same algorithm is not going to work. Well, it is basically, it's not going to be efficient if you want to run on it. But aside from efficiency, we say that you need omega of n additive error anyway. And how these, a lot of like these combinatorial lower bounds work is that you introduce a class of graphs, and then you say that if you want to have privacy guarantees, basically you can't have low error on all of them. Okay, so what is this class of graphs for us? So we have our terminals S and T, and then we have n-2 nodes in between. And for each of these nodes, like VI, I either attach it to S or to T. So I get 2 to the n-2 different instances, right? Now, for example, this one, the mean state cut is SV3V5. Okay. Now let's take a neighboring instance. So instead of having V3 being attached to S, I attach it to T, right? It's like neighboring in a two-hop way. It's not exactly neighboring, but we can think of it as neighboring. All those like guarantees kind of still hold. The mean stick cut here is going to be SV5. Okay. Now, what can I say here? So first, I know that any DP algorithm should output SV3V5 with similar probabilities on these two. Oh, sorry, yeah.
These black lines are the edges?
Sorry, say it again.
These black lines are the
Yes,
edges?
yes, yeah.
What do you mean by minimum cut here? Because they are already disconnected.
Well, I have to find it, right? I want to output, like, let's say if I just output that.
All right, we
Right?
don't know it. Okay.
Yeah.
Okay.
Like, I mean, I know it, but I want to output in a private way. I don't want my adversary to know, oh, S is attached to V3, right? Yeah. Any other questions on the instance? Okay. Yeah, so from DP, the definition of DP essentially, what do we know? We say that, okay, any DP algorithm should output SV3V5 in these two graphs with similar probabilities. Okay, that's what it said. And also any DP algorithm should output SV5 in these two with similar probabilities, right? But then we want to output SV3V5 in the left graph with higher probability because it's the actual answer, right? We want to have some accuracy. And we want to output SV5 in the other graph with higher probability because that's the actual answer. That basically says that all these four probabilities should be roughly the same. Okay. I'm really like, this is a really like hand wavy argument, but do we all agree on this? I want to prove that I need omega of n.
Then what problems both be the same? And both of them are gonna output us.
Well, no, let's say, I mean, I'm not allowed, I just want to like say that each of these VIs is going to introduce like, so they have to roughly be the same, not because of the additive error allowing, it's more because of just like the DP properties. The additive error is on the, it's on the accuracy side.
And on the right, I want to output SV5.
I want to output that with like, if you consider distribution of like my outputs that I can do, well, ideally, I want to have a high probability for that, a higher probability for that, because that's the correct answer, right? Yeah, then I want to basically like, okay, I want to, if I'm allowing an additive error, I'm kind of like, I can output anything that is close to this with high probability. Is that what you're saying?
Exactly, like in this particular example, I will just always output SV5 for both of them.
Yeah. Like for that, I can say, consider the graph that V5, instead of being attached to S, it's attached to T, right? Those are neighboring too with this, but V5 is not now in the mean state cut.
Not even
If you're gonna like always put V5, that's gonna be problematic down the line, right? This is essentially what we're gonna say, yeah. So we want to kind of say that it's like putting V3 here in the solution or not putting it, you are kind of doing it with similar probabilities. And like, so it's kind of each of these nodes is adding a constant error. Like you can't you can't get away with that. And that's why you get like omega of n error. Again, I'm just trying to like give you some intuition. This is in no way like a proof.
Is it like,
Sorry?
are you using something like hacking?
Yeah, essentially. Yeah. I mean, there are like, a lot of like lower bounds like this. In particular, this one is, we got inspired by a similar lower bound for correlation clustering. It's in this paper by Conrad et al. In NeurIPS 2022. The argument actually, like, they're very similar. The graph class is a bit different, but yeah, essentially the same idea. So it like appears quite a lot.
Do you know if does lower bound hold under a prox or are there other?
Yeah, it holds for prox too, and also for multiplicative error, because the actual mean state cut value is 0. So even if you allow multiplicative error, like, yeah, you can't do that.
Is there any intuition why epsilon does not appear in the rule?
To be honest, we didn't try hard to like also have a dependence on epsilon. And I remember for a while it wasn't easy to have epsilon lower bound, but these days basically people have figured out how to incorporate epsilon. It's not trivial on how to like, yeah. We can probably, if we try hard, we can probably like also have it, yeah. Okay. So let's say the other side. This error may not make sense if your graph is unweighted because you just output like S on its own, that the cut that detaches S from everybody else. So let's think of the graph as weighted. It's still gonna be a high error, but we want to like at least have a matching algorithm. And it's gonna be also like quite simple. So how do we do it? We have our graph, we have our S and T. So we're gonna change the graph a little bit. We're just gonna inject some simple noise. So for every node V, we're going to add an edge from V to S, drawn from exponential distribution. And this is not going to be a noise with mean 0, okay? We're kind of used to that, but we're gonna see the symmetry in a bit. Then we're going to add an edge between V and T, and we're going to draw the weight from exponential distribution again, okay? And that's it. Then just run any mean state-cut algorithm you'd like on this, and I'm gonna claim that it's gonna be private. Yeah.
What is exponential distribution of
E to the I think minus 1 exponent, yeah, e to the minus is it, I think 1 over epsilon in there, x squared over epsilon. Oh,
We sample weights from this.
yeah. What do you mean?
What does it mean to sample from exponential?
Yeah. It's like just literally from the distribution, just like take your noise according to that. Like epsilon, I think appears in, I think it's the mean, if I'm not wrong. I don't remember if the mean or the variance, but yeah. Like the same as if I put like Laplace with a
What is the definition of exponential?
distribution.
The PDF should be
Yeah,
like exponential lambda is lambda times e to the minus lambda times x.
that. So you draw x from that. Yeah. Does that make sense?
Okay, that's fine.
Okay.
But
How do I, yeah.
is it like the distribution that you succeed in probability epsilon and you repeat until you get a success, or is it?
No. I literally just draw a number from this distribution and add it to the weight of that edge. Literally that. Yeah. Makes a little bit more sense. Okay. Yeah, so this is the algorithm, and I'm going to claim that this is private, so it's 4 epsilon dp, and I'm going to get an additive error of order n over epsilon. Okay. So if you're a bit familiar with like differential private algorithms, most of the time you can't really get away with not adding noise to every pair of nodes, right? Like you have to add a noise to all of that, and then that's usually the like doesn't give you any good guarantees. But here we say, okay, you actually don't need to do that. You just add noise to basically linear number of pairs of nodes. So why can't we get away with that? Again, I'm just gonna like give you a very rough intuition of like why this works. Any other questions on the algorithm? We're good. So let's consider two neighboring graphs, G and G prime, and they differ in one edge UV. Okay, everything else is the same. Now, So for fixed terminals, we still have like 2 to the n minus 2 different cuts, right? How are we gonna argue about the distribution of the output on all of these cuts?
Select noise index.
Hmm?
Is this select noise index?
Yeah. What do you mean? Like,
Or you can do mass selection. Say you have a vector.
Yeah.
And then you can select and the neighboring relationship is that L infinity one.
yeah.
And then you can add the exponential noise to each entry, and then the mass is eventually by it.
I mean, I want to output like the cut, right?
Yeah, but you can view the cut as a vector.
Yeah. Okay.
You can view the cut as a high dimensional vector. The dimension is e to the power of n minus 2.
Yeah, yeah.
And then you change one edge, you can change each coordinate value by at most 1. Then you can add exponential noise, or you can add a phase noise, or you can add more noise to
Yeah.
each entry, and then
Yeah, but in that case, when you change one edge, a lot of different, I mean, SD cuts are gonna change their
yes,
value, right?
that's that noise index. The neighboring definition is that they're out infinity one.
Yeah.
Two vectors are neighboring if they
Yeah.
by the out infinity not by m.
So like, what error would you get?
Or the same error.
Yeah. 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 Okay.
So I guess we also work by adding the phase noise and component noise. The same argument will.
The same. Okay. So the reason why we didn't do Laplace was that we kind of wanted basically what appeared for us was the subtraction of 2 exponentials, and that's Laplace. That's where like the Laplace kind of appeared for us. Yeah. But yeah, that's a nice argument. This is like kind of gonna be a more combinatorial one. So we basically said that we basically say that not all of these cuts are gonna be important. Like, sorry, did you have a question? No. Only just 4 of them are gonna be important. So why is that? You can divide your cuts into 4 categories, and depending on where U and V are, okay. If they are on the S side or T side, basically, and then just forget about the randomness I added for a sec. I want to claim that if in each of these categories you order the SD cuts by their values, then this ordering doesn't change when you go from G to G prime. Why is that? Well, the first one, UV doesn't even appear in the value of any of those cuts. So like, well, they have exactly the same values. So, okay. The second one, when you go from one G to G prime, this cut value is changing by exactly the same amount for all those cuts, right? So again, the order is going to be, their value is differing, but all by the same amount. So the order of the cuts are going to be the same in both of these graphs. So I'm gonna, in each of these categories, I'm just gonna order all my SD cuts according to their value, right? And I'm just claiming that when you go from one graph to a neighboring graph, like here, this ordering is not gonna change.
Inside each.
Yes, inside each class, yeah. So what I'm essentially claiming is that only 4 cuts are important. The mean cut in each of these 4 categories, because one of them is going to be my mean SD cut. So I kind of just need to argue that, okay, like with similar probabilities, similar cuts, I'm going to output like the same cuts in both of these 2 graphs. And that's kind of why we can get away with just like adding noise to order n many pairs of nodes instead of like everyone. So here I'm adding noise between roughly 2n pairs of nodes, right? Right. One classic thing that you can do is just like that almost never works. Just add noise to all the pairs, right? Then your graph is private. Just solve any algorithm you want on it, solve any problem you want on it, right? Yeah. So yeah, this is kind of, I wanted to give an intuition of like why we can get away with just like this, right? Um,
Noise you add over a fixed pair is Laplace noise of 1 over epsilon.
it's exponential, but what appears, yeah, exactly. When you subtract, like, kind of the noise between V and S minus V and T is gonna be like Laplace. That's where like Laplace comes from. Okay. Any questions before we go to the next problem? So for this one, we claim that, okay, if now you want to output all of the pairs of mean-state cuts, then your additive error is just going to blow up by polylog factor, okay? Again, we're kind of like the first people to look at this problem, but I've just listed some of the maybe relevant ones. The first one is just the result that I talked to you about. The other two are like some of the all cuts results. Like we know that we can query values like from these all cuts results, but anyway, the thing that I want to point out is that your error bound is still gonna be like order n to the 1.5. Okay, and it's gonna be too high for us. We want to kind of like beat that. So let's see how. If like, again, you're a bit like, well, one naive thing to do is that, well, we have like an algorithm for mean-state cut, just run it for all pairs. Like, what do you get, right? So even like to use that, we need this tool composition from differential privacy that says if you have like K epsilon dp algorithms and you apply these adaptively in sequence, you get an algorithm that is K epsilon dp. And you can do a bit better if you're fine with approx dp, you can make this K root K. Okay. Now, this means that if we apply that private mean-state cut algorithm on the n-choose-2 pairs, using advanced composition, our error is actually going to be order n squared. So the order n comes from, well, the error that we had from mean-state cut. The other n comes from square root of n squared. Okay. So it's not really good. What can we do? Well, one thing that's great if it exists is that if we could solve all pairs mean-state cuts with only polylog n invocations of mean-state cut, then we can do that. And luckily, this exists in the non-private world. Okay, we use this like in particular, we use this result of Abu et al. In 2021. They basically construct, their goal is to construct a Gomer-Hut tree fast. And they do that because they want to solve global min cut fast. Okay. But, well, we basically use this result because they essentially don't use many mean-state cuts. All this sum of the size of all the instances that they run mean-state cut on is order n polylog n. It's exactly what we want. It doesn't mean that like now, okay, great, you just like add noise, we're done. It's like, again, it has like, this algorithm is not like exactly simple. There are like still a lot of steps to it, but yeah, essentially we use this algorithm as our base and like we can make it private.
This results with Justin, right?
Sorry?
This
Yes,
results-
yes,
okay,
yeah.
It's not a black box.
No, it's not a black box, yeah. We have to open up the algorithm.
Not really enough so that we can open the black box.
I mean, if it was literally like running a bunch of mean-state cuts and doing nothing else, right? Then yeah, but they do a lot of other stuff in their algorithm. Yeah. Then this wouldn't be a paper in that case. So yeah, I didn't want to put a lot of time on that result because the next one I'm more excited about. So I've been telling you all these like additive error bounds. Can we do all cuts in this bound? And unfortunately not. We can do it in n to the 1.25 additive error. And in fact, not even this, we have a multiplicative error here. Okay. So again, let me tell you a brief story. This problem has been around for a while, so there has been some really nice work on it. Again, this table is in no way like complete. The first result that I want to point out is this inefficient result, but gives us really good bounds. So it's an exponential time. It is a pure DP algorithm with multiplicative error, or it has multiplicative error 1 plus alpha, and it has an additive error that is almost linear. There is alpha there too, I've just removed it for simplicity, okay? How does it work? So from sparsification theory on graphs, we know that any graph G, for any graph G and any parameter eta, we can find in polynomial time another sparse graph basically with order and log n over eta squared edges that preserves all the cuts with 1 plus eta approximation, okay? Well, great, let's find an approximation of this guy, right? Well, how can we do that? We list all sparse graphs with the sum of weights roughly the same as like our original graph, and then we use exponential mechanism to output one of them, right? This is great. If it gives us those error guarantees, unfortunately, it's going to be exponential time because there are exponentially many of these graphs, and we don't have a way to trim that list to like polynomial size, okay?
Does this algorithm also work for spectral sparsification or just?
No, I haven't seen that, yeah.
So it's like open whether there is a exponential time getting this accuracy for spectral?
I think so, if I'm not wrong, yeah. I'm,
All of this is spectral.
would it work? Okay,
There are spectral sparse with a small number of edges and a small weight.
this, yeah, okay.
Just-
If, yeah, then this would work, yeah.
None of the like the common.
No, it wouldn't,
Efficient ones not for quite exponential.
yes, then, yeah, it then should be the same. They don't phrase it for, this is like, okay, also, I'm not exactly sure if this is like kind of an old algorithm. The first people to mention it formally is Elias et al. In that paper. There may be this, but they don't really claim that this is like theirs. So it's kind of like, yeah, that does, yeah.
Even then, they're not paying.
Yeah.
The papers like Jana and Yintaz and amongst other people, right? Do you know what I mean?
It's like Elias Kapralov.
Ultimately,
I think so, yeah. So this is kind of the ultimate goal, to make that exponential being polynomial and get the same guarantees. But we're not there yet. So what do we have? This first one is just add Laplace noise to all the pairs. Gets us order n to the 1.5 over epsilon. It's going to be polynomial time, but it's going to have negative weights. So that's not something we like. We want positive edge weights. Then Gupta et al. Came out with this algorithm. They basically they use this framework called iterative database construction algorithms, and they don't output a synthetic graph, but they essentially output like data structure, let's say, that you can query different cuts from, okay? Then there's this work of Aurora et al. That they get a multiplicative factor, and their error guarantee is in terms of the size of the smaller side of the cut. It's going to be again n to the 1.5 in the worst case, but this is nice because for smaller side cuts, we get kind of a better error bound. And remember this form because we're gonna use it in our algorithm. This result of Elias et al. That we said is optimal if the multiplicative error is 1. And it's again root mn over epsilon. And they're all basically n to the 1.5 for dense graphs. So that's why our goal is okay, we are going to allow multiplicative weight, and we want to beat n to the 1.5. So how do we do it? The key here is using expander decomposition. What are expanders? So expanders are a psi expander has this property that for any cut C, the weight of C is at least psi times the smaller side of the graph. Now, this is very similar to that Aurora et al. Right result, so we're going to use that. But anyway, well, our input graph is not going to be expander, right? So what do? We use an expander decomposition, which says that for any parameter psi, we can decompose the graph into components we want to VK such that the induced subgraph on every component is a psi expander. And the graph in between them is sparse, basically. The sum of the weights is like n psi, okay? Now, okay, so we also know a good algorithm on sparse graphs, right? So ideally, we want to have an expander decomposition, use that Aurora et al. Error bound on those components. Why? Because the idea is that we can push the error to the multiplicative, because the expander says that the size of your cut is going to be a lot. It's going to be big. And this says that your error, the additive error you're going to get is kind of similar to that size. So you can then push it to multiplicative. And then for the graph in between, okay, we have a good algorithm for sparse graphs, so let's use that. We can do it, except that we don't have a private way to have an expander decomposition. We can't just run an expander decomposition because on two neighboring graphs, it may give me two different decompositions and well, I can't work with that. I want it to give me basically similar ones. How do we?
It's just a subroutine inside the map.
Yeah, well, basically I want, so this is a subroutine, yeah, but I need that to be private as well. So I need the distribution of different decompositions it's going to give me to be the same on two graphs. If this is violated, whatever I do may not give me privacy afterwards.
Because your individual is solving on the one.
Exactly. Yeah, that's my goal, right? Yeah. Yeah. So it turns out that you can just make your graph noisy and then run a non-private expander decomposition on it. It's not it doesn't directly follow that the result is an expander decomposition for your original graph. But we can prove using a bunch of different papers that, okay, essentially this algorithm works. That you make your graph noisy and you run an expander decomposition on it. The parameter, though, should be at least a bit bigger than square root of n. For that, we can solve this. And this is essentially the algorithm that I kind of told you on the previous slide. So what do? We have our input graph. We first make it noisy using that result of Aurora et al. So to remind you, it's the third row. It had that nice guarantee that looked like expander guarantees. So we use that. We make it private, but just outputting this is not going to be good enough. It's not going to give us large errors. Then we use expander decomposition on it. And we say that this expander decomposition is going to be private. Then we're going to say, inside each of these, we're good, basically. Because of this result of Aurora et al., we're going to be good. Then for the bit in between, those noisy edges are not good. So we're going to take the noise away. We're going to look at the original edges. And then we're going to use that result of Elias et al. Root mn over epsilon on that, okay? And roughly speaking, where does n to the 1.25 come from? The expander decomposition part, the inside, I just get multiplicative, so no additive there. And then the graph between them is going to have n to the 1.5 edges, basically. Or the sum of the weights is going to be n to the 1.5. So then if you put n to the 1.5 instead of m there, you get n to the 1.25. That's basically where it comes from.
So why was that the right balancing? If you always get multiplicative here, because psi enough such that they're only have.
The problem is that your psi should be at least root n.
Or to get a private.
To get a private expander decomposition, yeah.
So if you have a better private expanded decomposition,
then that's great.
really you don't care about the error inside these things, they even not.
If you can still push it to multiplicative, then
What can all this?
well, one, we don't have a way to make it have smaller psi than square root of n. But yeah, basically if also the algorithm of Aratal has that root n in it as well, right? There's a root n times s there. So if your psi is smaller than root n, here you get like a root n, so you can't really push it, right?
So for instance, if my input is a psi expander for psi to be roughly 1/n. It's a my input itself is
Yeah, yeah.
then you get n.
I think that's for 1/n, if like you can get a private one. You can't use that, well, for inside, you would need another algorithm, right? Yeah. Yeah. But our idea was to kind of like do this. Well, yeah, my next slide is actually the open question. So yeah, the first question is like, let's do this. Well, n to the 1.25 doesn't seem very tight, right? Let's make it order n. And one way was like, maybe we can use this expander decomposition idea a bit recursively or something like that. Well, so far it hasn't worked, but yeah, so we think that's the right answer. And the second question is one that I kind of alluded to. So for the problem of global min cut, this is a bit strange because like if you're allowing pure DP, then it seems like we can't get an algorithm that is not even like log n over epsilon, but additive error just like sublinear. And it's like just weird that we can't get that. If you allow approx dp, then yeah, we can get log n over epsilon. So yeah, this is like another interesting open problem. And yeah, that's where I want to finish. Thank you.
Questions? Say a bit more about, so I'm very curious about the first question.
Yeah.
Like what happens if you start doing expander hierarchies and recursive wise, for instance?
I mean, again, well, the first problem is that we can't make psi smaller than root n. Basically, like if we do the same algorithm, make things noisy and run a private expander decomposition on it, like, yeah, we can make it work for smaller psi. So that's the first bottleneck.
Is that I find it very hard to believe a single edge can change. Like expanded decompositions are so robust. You can remove an edge and nothing changes in the decomposition.
So we didn't we used another algorithm. We kind of did it a white box way, but we didn't get too much into the algorithm. So yeah, maybe like if you actually focus on that, yeah. Something else. Yeah. Yeah, in that sense, like that's kind of saying, yeah, I feel like you remove or add an edge, kind of the guarantees still like kind of almost hold. But yeah, it's like the other problem. We kind of want the algorithm to just output the same thing. Like, yeah. Yeah, we don't believe that's like you can't push lower than root n. It's just tried a little bit, we couldn't, but we didn't go into a lot of different expanded decomposition algorithms there. Yeah.
But that's not even the bottom. Even if you do that, still you won't get this ordinary time.
Yeah, there are other bottlenecks. For all of them, there are some ideas on like how to, yeah. So they're not bottleneck, like they are all like not hard bottlenecks, but all of those tricks don't work together yet. Yeah. Another way to look at it is like from, spectral approximation, because you get like results for cut as well. And the results there are also not optimal, I don't think, yeah. Especially like if you pay attention to how sparse your graph, like, yeah, your graph is like bounds in terms of M or, yeah. No, no, not really. Not specifically for sparse cuts, yeah. No, we thought a little bit on that as well, and yeah. It's a surprisingly hard problem, and we believe the error should be quite low, but yeah, there is still no algorithm for it. Yeah. Yeah, that's another nice open problem.
Another question? Oh, that's time, you know.
Thank you.